math. Hello, hello, hello. Technical difficulties aside, let's try and do some more math. So take a look at number 7. We're supposed to find the mean, standard deviation, and according to the range rule of thumb, if we look 2 standard deviations on either side of the mean, that should contain 95% of the value if it's normal. If otherwise, Chevy Chev says what, Taryn? Right, 75%. So it's going to be somewhere in there. Now, number 7 is binomial, so I drew a picture of this. And here we go. Down here in a program called GeoGebra. So this is a picture of not a normal distribution, but a binomial distribution. Sample size or number of trials is 300. Probability of a success is 48%. And it's this red, this is a red histogram, right? That looks like a normal distribution. And it's almost smooth. I mean, TI resolution, this is pretty damn good, huh? On a computer, not so smooth, but that's okay. Area inside, area of all these little stacks into these big ones here, all of the stacks add up to 1. What I calculated right here, the 0.05, is roughly the probability of the highest of these stacks. The highest stack will be the mean of the distribution. How do we find the mean? Excellent. It's the number of trials times the probability of a success. And 48% of 300, I'm pretty sure, is 144. So what I asked for from GeoGebra here, come on GeoGebra, you can do it, is to calculate the binomial probability. Here it's called binomial dist. On the TI it's called binom PDF. On Excel it's called binom dist. And I said there are 300 trials, probability of success is 48%, and I want x equals 144 exactly only. It's not cumulative. That's what the false means. And GeoGebra says it's about 5%. I'm going to choose OK. You can see on the graph that kind of makes sense, right? Here's 0.1, 0.06, 0.04, and the highest stack appears to be right about between 0.04 and 0.06. I went to Google and I asked Google to calculate the same thing. Binom dist. Here they want x equals 144. 300 trials, 0.48 is the probability. False means I only want a single value, not a tail. And it says 0.046. If we round that to the nearest tenth or the nearest whole percent, I get 5%. Okay. Why do I care about all that? This problem here again. So we have 300 subjects, 300 trials. Probability of a positive result is 48%. What we want to know here is what is the mean? Okay, well that's n times p. That's 0.48. I also want to calculate the standard deviation. Let's do that. I need some kind of calculator. And according to the formula, I want to get the square root of n, 300, times p, 0.48, times q, 1 minus that, which would be, what, 0.52 on a good day? And according to Google, it's about 8.7. So next we need to take that mean and standard deviation and see what's two standard deviations on either side of the mean. So we have a standard deviation of 0.87-ish. Since these are whole numbers, remember we take it 1 decimal place further. So let's get a new page. Oh, crazy. I'm supposed to take up the whole sheet. Anyway, so mu is NP, which is 300 times 0.48. And to the best of my arithmetic ability right now, it's 144. according to Google Spreadsheet, sigma, which is the square root of 300 times 0.48 times 1 minus 0.48, 0.52. That is about, oops, wiggly equals 8.7. So now what we want to do is we want to figure out on the left side, what is mu minus 2 sigmas? And on the right, what is mu plus 2 standard deviations? So what's that going to give us? If we double that, that's going to give us 17.4. If we add that on to 144, that's going to give us what? 151.4. And on the left, if we take that away, we're going to get what? 6.126. All right. Looks about right. All right. So what we want to do is check which values are between there. So that's going to be 127 through 151. And so then outside of this range, that's going to be unusual. Why is that? Well, this is relatively normal because the mean is close to 1/2. Sorry, the probability of success is close to 1/2. And it looks pretty normal anyway, right? It's a nice bell shape. Whoa, whoa, the pen's freaking out, sorry. Uh-oh. Danger. This is trouble. All right, so anyway, outside of this range we have trouble. So if x happens to be less than or equal to 126, or if x happens to be greater than or equal to 152, that means these guys are in the tail. This tail on the right represents about 2.5%. The tail on the left represents about 2.5%. Given that this looks pretty normal. Now we could check the empirical rule, and that's a little tricky on binomial distributions. Let's go back and look at the GeoGebra graph. So on the GeoGebra graph, I'm just going to plot those numbers. Let's see. The marker number is, let's call them 126 and 152. So x equals 126, x equals 152, and it looks like I made a mistake. Those should be pretty darn symmetric. Ruh-roh. So let's go to our calculator here, and we want to take 300 times 0.48, 144, and then we want to take that number plus twice the standard deviation. Something went wrong in that calculation. Plus 2 times the standard deviation. Oh, 161, I was off. That's good. It's always good to check yourself. So we're going to move this guy to 162. Oops. That looks more like it. All right. So what we've just calculated is that the tail probability here appear to be in the point at the 2.5 range in percentage. So we're going to double check here. I'm going to do a binomial calculation. So I'm going to use the binomial distribution. Number of trials is 300. Probability of success is 0.48. My variable value here, I'm going to use the lower tail, 126. and cumulative true, because I want to calculate the tail this time, not just an individual. And so GeoGebra says it's about 0.2% is the probability that only 126 out of 300 people test positive when they actually have used marijuana in this case. Let's up the rounding a little bit. Let's go to 3 decimal places. Most days my mom can handle that. 2.1% is what GeoGebra says for the left tail. Now for the right tail, I have to do a 1 minus, because GeoGebra and Excel and the calculator only do left tails. So 1 minus the binomial distribution. So here on the calculator, you would use binomial CDF. Number of trials is 300. Probability of a success is 0.48. Variable value in this case is 162 or higher. And Boolean true. Now on yours, if you use the CDF, you don't need the true. You will just have your particular numbers. Enter. And GeoGebra should give almost the same thing. It's a little bit off. Well, maybe my lens is off. Let's double check that. We want to know what is the mean minus 2 times the standard deviation. And GeoGebra says, yeah, no, that's about what we came up with before. Okay, that's okay. So 126 and lower is the left tail. 127 up to 161 represents what we consider to be normal within two standard deviations of the mean. If it's a Bernoulli trial, if it leads to a binomial distribution, and we're assuming it does here. So that is okay. So slightly skewed to the left in terms of the tail here. The mean is a little bit to the right. No, let me see. Sorry. Skewed left because the mean is a little bit below the center value between 0 and 300. Right? Instead of being 150, our mean is actually 144. So that means there's more probability to the left of the mean than to the median. Sorry, there's more probability to the left of the median, 150, than to the right. Skewness is tricky, especially on a graph that looks so darn normal. But here we can see there's a little less probability in the right tail than there is in the left tail, even though we symmetrically place 2 standard deviations on each side of the mean. Okay? So this line D is exactly 2 standard deviations to the right. The line C is exactly 2 standard deviations to the left of the mean. And we have 1.6% on the right tail. So again, unusual events on the right in this case, unusual events on the left in this case. All right, that's kind of a guideline on how to play with mean and standard deviation for a binomial distribution. We'll go over a couple more problems on Wednesday like this and move on to the normal distribution, which this very much looks like. Ta-ta for now.